will be given by Professor Philip Kim from Harvard University. Professor Philip Kim, can you start the sharing the screen? So the talk title is Toward Universal Quantum Computing Using Parafermion Induced Superconductivity in the Fractional Quantum Hole Edge. Okay, let's welcome the speaker together.
Thank you very much. Thanks, Chairman. All right, it is my great pleasure to deliver the talk, although it's virtually. I hope that I have a chance to visit Korea fairly soon. So I know that this is a quantum conference week or quantum, yeah, I think it's, I forgot the official title, but it's quantum week in Korea. And series of the very exciting talks about this quantum science and technologies and new opportunity. And I just try to align my talk in that directions. As two previous speakers in these sessions try to give the various different directions that can align it. And perhaps I probably put the too outrageous title, stretching the ideas a little bit. But you will see that in the motivations. There's a route that may actually produce some things that interesting quantum device for helping with the quantum computing. But real stories is in the second line, induced superconductivity in fractional quantum edges in connections with this the universal quantum computing idea. So this talk is the work is done by the many people. The major work is done by the Under Gur and the Yuval Ronen, two talented postdocs in leading to this project with help of many, including our chairman, that the Professor Gil Lee, when he worked with us, made a real pioneering work which actually initiated this the project. We have the strong collaboration in Ami Yacoub's group, as well as in terms of theory. Hassan Shaporian and Ashwin Vishwanath actually contribute quite a bit. Okay, so let me just kind of set the stage for the general idea. All right, so we know that in quantum mechanics, when we deal with the indistinguishable particles, and especially in the 3D, the quantum mechanics dictated that this indistinguishable particle, once you just exchange them or just kind of change their positions, then there are two kinds of the possibility. One, either it becomes a boson or the fermions, depends on the when you exchanges, the wave function changes sign or not. No other possibility exists that when material, the fundamental quantum particle is in the 3D or beyond the dimensions. However, when you just kind of confine this indistinguishable particle in 2D, there's something interesting thing happen in this confined two-dimensional space. In some sense that this exchange operation is related with the kind of rotating the one particle or the other and along the axis. So this winding becomes important, and because of this topological nature of the winding, there are other possibility actually is now possible other than boson or fermions. In general, when there is a non-degenerate ground states that got imposed, if the ground state is not degenerated, then the possibility when you just kind of exchange this particle, it comes with a phase, but it's instead of that phase, it becomes 1 or -1. There's a possibility this phase can be some, the integer fraction is possible. And this actually gives you the general idea of the non-fermion or non-bosonic possibility. It becomes even more exciting that if the ground state is degenerated, such that when you just kind of exchange its positions, there's a chance that this wave function can map into another one. And then this exchange operations will provide even just the unitary matrix that map the wave function from one to the other degenerate states. And all of these things in generally, that when you exchange this to particle, you come into the kind of not just a sign difference in terms of wave functions and other possibility. Often that this is in the 2D, the people just classify as anionic quasi-particles, and it becomes kind of quite interesting. Quite recently, there is a possibility, actually, just there is experimental observations that indeed this anion do exist in the many body systems. In particular, this non-abelian anions is quite useful in many regards because this matrix that map the ground state wave function. The other is matrix. In general, if you just do the multiple exchanges, since matrix may not just commute each other, there is a possibility then, in fact, making this kind of consecutive exchanges, you may not come back its own, but it actually keep mapping into the different type of the system. This can be actually well shown that, in fact, if you have the couple of these different non-abelian anyons, then when you just kind of keep exchanging their positions, in fact, this in the final state, although the configuration of the state looks similar, their quantum mechanical nature actually depends on in the past how many exchanges you have, or more precisely in this particular case, one can say that how many braiding you have, because that basically every time exchanges, you have some of the record that remaining in terms of this the wave function. Many-body wave function contains this history of past in terms of the braiding operation, and provides some of this topological natures. In fact, the people have been seeing that this type of this braiding operation of the non-abelian anyon is a way that you can install the quantum informations into the topological manner, in a sense, like that this really braid that we made out of the bunch of the string, the topological nature under this knot or braiding that we made cannot be just destroyed by just local actions. And this is a way that can provide, in fact, the protections coming from this topological nature. Why this becomes kind of necessary and interesting. Many people think that this type of the non-abelian anyon is one of the ways that you can produce this the quantum bits, qubits, that topologically protected. So in a sense, once you realize this type of the qubits, it is the vigilant onto any local perturbation, and therefore the one can build up this fault tolerant quantum bits out of it. I think that's kind of idea behind of that. And although there's no real demonstration has happened yet in terms of the making the qubit operation, if one can make this one qubits and make a few qubits, that certainly will revolutionize this the quantum computing area. And that's why that worldwide there are a lot of efforts to realize this the topologically protected qubits. So how we can do that? There are a few, the material platform has been suggested, and early on that people just think that so-called the even denominator, the fractional quantum of states, one can make in the high quality to the system, make it kind of one of the route to create this the topologically protected qubits. There has been a lot of the experimental efforts in there. More recently, there are some of the platforms that combine with the superconductor, such as a superconductor combination with topological insulator, or superconductor with 1D semiconducting wire with the spin-orbit coupling, or the superconductor coupled with this 1D ferromagnetic atoms. And these type of the platform, each of them can provide some sort of so-called topological superconductivity, which is based that kind of realize this the non-abelian anyon as an excitation. Often that people call the particular non-abelian anyons that produce in the 1D wire on this type of topological insulator is called the Parafermion. Probably you heard about that already, right? So idea is that is there a way that we can also produce this type of the non-abelian anyons or topological superconductivity in somewhat different material platform other than just what is discussed here. So one of the ideas is, it's already discussed a couple of times throughout this, this particular section. Maybe we can just use a 2D materials. In a sense, 2D material comes with many different flavor, like starting from the graphene boron nitride, metal dichalcogenide, or the even high temperature superconductor. In some sense, many topological 3D topological insulator is also Van der Waals system. So combining of this type of things, one maybe produce some of the interesting material platform to realize the topological superconductivity. One idea is just using the graphene, but just not just only using the graphene, but graphene plus something that we can just induce those kind of material platform. And that's kind of basically some idea that I'm going to present today. So graphene nowadays that one can encapsulate with the boron nitride and selectively etch this the stacks and make the contact. One can immediately make the extremely high quality two-dimensional electron system combine the graphene. I think like the gallium arsenide electron that in gallium arsenide, aluminum gallium arsenide interface, the one can reach the mobility of the millions or tens of millions basically limit by the size of the sample, mean free path, reaching something like easily tens of micron. And also, because there is no gap in the graphene, one can make the contact reasonably well into the graphene, including the contact with the superconductor. So that is kind of one idea. The other part is the quality of the graphene becomes high, and with the reasonable magnetic field, there has been demonstrations that you can make this the quantum Hall effect sets in the graphene, or perhaps even up to the fractional quantum Hall effect, many of them with a reasonable magnetic field with a reasonable density, such that you can make this quantum Hall integer and fractional quantum Hall effect becomes very robust, and that is one of the advantages one can utilize to realize the system. So idea to realize the topological superconductivity is basically, can we combine with superconductivity with a particularly fractional quantum Hall effect and come up with unusual the topological superconductivity in the system, which might be utilized for the topologically protected qubits. Now, the idea of combining that topological superconductor with the quantum Hall states has been around already, and perhaps in the topological aspect, first discussed with the Shucheng Zhang's the work about 10 years ago in the following way. In this particular case, that Shucheng Zhang's group thought maybe combining with the superconductor with the quantum Hall effect or anomalous quantum Hall effect. He used anomalous quantum Hall because the usually magnetic field in the required the quantum Hall effect may destroy the superconductivity, but in some sense the physics that they draw in is basically applicable for even for just quantum Hall system. Anyway, the idea is basically combining that superconductor with this chiral electron system with the Chern number 1 can easily create this the topological superconductivity, and especially in the defect of the superconductor, such as the vortex that thread into the system should contains the Majorana zero mode at in the vortex core. So basically, you can create this non-abelian anyons. It's on the every vortex you thread into the system, and basically manipulating these vortices, you can kind of create some sort of idea of the braiding of the system, and beautifully demonstrated in this paper. In fact, actually, just after this paper, the people just kind of push this idea kind of immediately soon, and there are a couple of groups that take it over this idea to the next level, and they ask that what if that you just kind of just not only proximatize that the quantum integer quantum Hall with the superconductor, but what if that you approximate the fractional quantum Hall effect with the superconductor? It turns out that Majorana fermion is a particular anyon in a sense that you basically braid that 4 times, then you get this kind of its own sign, or that basically you have the braiding this two that to come back to its own. But if you just generalize this Majorana fermions into the non-abelian in general, especially when you just assign that fractional quantum Hall effect the proximatize, it comes out the generalized Majorana fermion or non-abelian anyon, where that basically you have to braid the 2m times, where m is integer, then it comes back its own, right? When m equal 1 is a Majorana case, and then you basically go beyond many times, and basically this is a generalized Majorana fermion, often people call the Parafermions. And once you just kind of get into this Parafermions, and the theorists actually theorize already quite a bit, that around the similar times that there are many theory papers comes around. Unlike the Majorana fermion, we often call this Ising the non-abelian anyon, which we cannot create this generalized the universal quantum computing. If you use a parafermion, because you have the multiple ground states, so you can utilize this one to come up with the so-called universal topological quantum computing is possible. So I think that's why there is kind of some the excitement that realizing this type of the parafermions for universal quantum computing. Now, how we get there? So basically, idea is the first step is we should show that the existence of such the unusual quasi-particle, non-abelian quasi-particle, that when you proximatize fractional quantum Hall effect with the superconductor. So basically, that's kind of very first step. It has been tried out already in a couple of groups, I would say. The first try is here that Leonid Rockinson group at Purdue University basically put down the niobium as a superconducting contact on the 2D electron system they can get on the gallium arsenide, and applying something like a few Tesla, you can get already a series of this fractional quantum Hall effect. You can see that 3/5 and the 2/3, for example, and 4/7, right? And then they measured this group measured the effect of this fractional quantum Hall effect using this the superconducting contact as a kind of hoping that they can see that this the effect of the proximatizations. Well, they see that some unusual phenomena, but it was never be just kind of easy to detect this type of the phenomena reliably. Part of the reason is usually the superconductor can withstand such a high magnetic field, such as niobium nitride. They are refractory materials, which means it's very difficult to make the good contact with a semiconductor. And the contact transparency was a kind of really difficult part. So compare with this, the semiconductor heterostructures. Graphene encapsulated boron nitride is a good candidate. Maybe you can make the good contact, reasonably good contact with many different superconductors, including the superconductor which actually has a reasonably high HEC2. Indeed, in this experiment done in Glaffington-Stein groups and the Duke University, beautifully show that you can just make the graphene Josephson junction with the molybdenum as a the superconductor contact, and they demonstrating that they can get this the Josephson current when the integer quantum Hall effect is sets in. However, that as the name indicated, that Josephson current means that it's basically zero resistance. Two-terminal device in this case is the quantum Hall effect means it has the finite quantized conductance. So it's not just compatible with each other. Indeed, what they see that is in the middle of plateau, the plateau collapsed down to the supercurrent and come back, and it was a little bit random fashion. So it was kind of interesting observation, but it's a bit difficult to kind of show that whether this is really indications of the proximatize the quantum edges in the system. Now, there's a way that, in fact, one can demonstrate it unambiguously that your quantum edge can be proximatized. The way is that we can use so-called undriven fractions. Here, that idea is you the contact with the superconductor with the normal metal and send this current through this interface. At the interface, that electron or hole that carry the current in normal metal converted into Cooper pairs. And then if it's the electron, that hole should kind of retro-reflected and create this Cooper pairs. So in some sense, you get double the current when you send the current, which actually enhance the conductivities across the interface, which actually has been discussed by the Andreev in 1964, and ever since that there are many of the experiments actually demonstrate indeed that that's the case. So we can take this type of the idea of the Andreev refractions and apply onto the quantum Hall and ask whether one can detect such effect in the system. First of all, that one should come up with the right metal, right superconductors that can withstand high magnetic field and yet give it a really good the contact. Professor Kilori, that when he worked with us and he developed this kind of the recipes that are basically using the Thai niobium nitride of the stacks, one can make the fairly good contact onto the graphene that can withstand the magnetic field up to the say 12 Tesla. You can still get the enhancement of the conductance about 10 or 20%, which actually is probably good enough that we can test it out, this Andreev reflections onto this quantum energy states. And what we can do is simply that we set up this the contact with the four-terminal type of the geometry, and then we can measure both the longitudinal conductance and the transverse conductance or conductance. And typical that the quantum Hall, basically on the upstream, that basically you get the bias voltage V and V, but this is grounded, and downstream that we expect to see the zero voltage there, right? So we just repeat a very similar experiment that this grounded contact that replaced by the superconductor. And if this superconductor is thick, then of course when electron comes in, that will create the hole and electrons, a hole, and this type of the Andreev refraction is happening. Eventually across the interface or the peripheral of this superconductor and the channel, that you have so many conversion of the electrons hole repeated, and in the end of downstream, you get about the mixtures of the electron hole. And if you measure the potentials, basically electron hole will give you the different opposite sign of the potentials, which will average out more or less equal to 0. So in fact, like the Rockinson C, that when you just make the superconductor context and make this measurement, you don't necessarily see the big differences in that whether it's a superconductor or it is normal metal. However, ingenious thing is happening that when you make that this superconductor is very thin. And what happens is then instead of when electron comes in and coming to the converting to the hole through the Andrew process, instead of actually make these holes in the same side, since the superconductor is so thin, it can grab the hole from the other side and create this hole, can just kind of travel through the downstream and just provide this negative potential of the downstream. So this is a way that we can, in fact, in principle, can detect this the Andrew process. And once you just kind of detect this type of the negative signal in the downstream, and that is a strong evidence that indeed we start kind of do the superconductor is in fact start kind of proximatize into this quantum edges. Indeed, this experiment was done. Then when the Gilho was in the group and beautifully demonstrated when, at least when you get into the integer quantum hole, and when quantum Hall effect sets in, if you measure downstream potentials and converting towards this resistance by dividing by the current, you get this all kind of strong negative signal, strongly indicating indeed that we are getting this the undriven reflections into the system, and which actually can be interpreted that you have the upstream the quantum edges and downstream quantum edges. Basically, they are proximatized by the superconductor, and like this 1D wire that where that you have this two counter propagating state is proximatized, create the Majorana fermions, and this the Majorana fermion is created, and that actually mediate those kind of the cross-Andrew reflections. That's such that it getting the negative signal on the downstream. So that was kind of something that done about kind of 3 or 4 years ago that we just kind of showed this one. Now, the next goal is, can we actually push this into the fractional quantum Hall effect? Well, to get this experimental done in the fractional quantum Hall effect, we have to increase this the quality of the sample even further. So previous experiment was done, the graphene not fully encapsulated, or it is encapsulated, but at least we used the gate made of this conventional metal or the back gate. And it's been known that to get this extremely high quality of the graphene channel, we need to encapsulate it with the graphite top and bottom gate. So to make the completely van der Waals the stacks to make this device. So in fact, we just made this the top and bottom graphite gates with the very similar structures. Now we kind of carefully etch it. So device is kind of rather kind of beautifully designed, but essential part of this device is we have the normal metal, but important part is this is a niobium nitride electrode, and especially this is a very narrow. And you see that around this niobium nitride, we can carefully carve it out the top gates such that it allows to control the separately this superconducting region. Then you will see that is also important the aspect of this type of the measurement. Okay, so once we have this type of the device, we can measure the very similar way. So we just send the current from upstreams and ground this the superconductor, and we just monitor these downstream voltages, and that will provide us that crossover refraction signals. So what is the result? So the result is the following. Oh, by the way, so the way that also important quantity I'm going to discuss is so-called this probability of the cross-Andrew reflections. Basically, if you just go for the integers, especially there are many edge states, you want to see that each of the electron impinging onto this contact through the various different type of your edges, that what is the probability of this getting cross the Andrew reflection, and that probability is important, and that's roughly this the cos signal divided by, I'm sorry, that this is not car, the cos signal divided by the RXY will give you the probability of this Andrew reflection, which is an important quantity I'm going to use from now on. Okay, So here's the data. The magnetic field with the gate voltage is in the channel, right? You can see that there is RXY shows this nice band-like behavior. So nice quantum Hall sets in. And this is the cross-under refraction signal in terms of the resistance, right? The blue is basically negative value, which means that this nice, the stripes of the blue that fan-like, indicating that we have this car process happening everywhere, right? But exciting part is not only integers that we are seeing, but you can see that here that all these fractions, 1/3, 2/5, and 2/3, and 5/3, they are all kind of negative values, showing that indeed we have the very strong car for the fractional quantum effect. So that is very good sign, right? Indeed, if I just kind of show you the RXY shows this plateau at the taken at, I guess this is 13 Tesla, you see that this deep negative values appears on all these integers, much bigger than in some sense that in the integer value. So it's clear that fractional quantum effect also do show this the car signals, and which actually you can easily check it out by increasing temperature to quickly wash it away. So it is a kind of real things, right? Second part interesting is if we just kind of for now slightly low magnetic for Tesla, so you don't see the diffractions, but the integers, you see that there is an interesting progress. In the lower filling fraction, we have the strong car. In fact, it turns out if I just divide this R car with RXY, I mentioned that this is roughly that probability of the cross-under process. They're all kind of constant in there, right? If we just do the proper value of this one, that's about the percentage of about 1% or 0.5%, depends on the devices. But amazing part is they're extremely robust. All this filling fraction, they have the same value, right? And with change of the magnetic field, this car process is not changing. Something very, very robust in this car. So what is really happening? In fact, if you just kind of go through the theoretical calculation, turns out the theory require, as we expected, the strong spin-orbit coupling that provided by the superconductor is required. Since we have the niobium, it will provide the strong spin-orbit couplings there. And once you just throw this spin-orbit couplings from the superconductors, basically it turns out that this the cross-under process will create this the gap in the spectrum, right? And this spectrum, in a sense, is protected, or there is a gap opens up by the spin-orbit coupling. But inside of this gap, you have the basically 1 Majorana modes happen. And as you increase this number of this edge state, it's basically just kind of keep making copy of that, right? So in some sense, every the gap that opens up by this integer quantum or edges is basically protected by the topological protections, like the Parafermions does, and that's the provide this robustness of this car probabilities, regardless of the fractions, the filling fractions, as well as magnetic field. So that's kind of good to know, right? But second part is now we can just focus on that what happens to this the fractions. So similar way that we can just take the focus on these fractions in high magnetic field, then we can just kind of get the probability of the car, right? It's overall clear that once that the fraction is set in, let me just kind of take this one. Once the fraction is set in terms of the RXX, it becomes clear that you have the huge R car start to shows up, and even after you just normalize the RXY, you start to see the probability of getting the cross-under reflection is even stronger than integer cases. Most of the integer in this particular case, we get about the 3% or less, right? But once you get to certain diffractions, such as 1/3, for example, and 4/3, you get the kind of about the factor of the 3 or 4 enhancement in this fraction. So something unusual things happening, especially certain fraction of quantum effect. What is really going on? Right. Okay, I have the 5 minutes already passed. Okay, yeah. So I'll finish up in very soon, right? So this robustness of the car process, in fact, in certain fractions, that tells us that indeed this process is rather different from integers, right? And what we believe happening is that to explain such a robustness of the car process on fractions, basically we are being forced that we are really making this proximity effect onto this fractional the quantum Hall states directly, right? And that's basically the major ingredient actually required to create this parafermions. So I know that this is a rather indirect evidence, but strongly indicating that such a strong the Ka process interactions, in fact, that they start kind of support the idea that we may actually kind of get into this first step to creating this parafermionic the quasi-particle state at the end of this the quantum Hall edges. This process actually can be even just kind of viewed in the following way, that as I mentioned that we have the small cut around this superconducting area that we can separate the ligated, and we can actually compare how this Ka process is changing as you just kind of changing the doping near the superconductor. It becomes clear that in integer cases that we can see that pinching up to the accumulations around this area, the Ka process is only just to disappear in the pinching up cases. However, just doing the same experiment in the fractions, like the 1/3 states, you can clearly see that as you just change this, the edge state configurations, you can see both the pinchings and accumulations, that only that when you have the in between the accumulation pinching, you can sterilize this very strong the cross-under reflections, which actually also agree on that we have the making direct the proximity effects onto this 1/3 edges, and certain fractions such as the 2/3, which is particle conjugated, whole conjugated fractions, which actually has shared both the integer and the fractional quantum Hall type of natures. You see that they actually coming into the very similar nature like this, half of the fractional quantum Hall effect plus half of the integer quantum effect. All of these things start indicating indeed we are on the right track. So I don't have the time to just discuss some more of the detail. But we are on the right step. The very first step start to demonstrate indeed that this type of unusual quasi-particles can be created by approximatizing these fractional quantum Hall edges. And there are a few of the experiments we are just kind of planning to do, just to really unambiguously demonstrate those kind of existence of those particles, as well as the manipulation of those particles. So that's kind of some of the experimental comments. Thank you very much for your attention. Sorry for the run of time.
Thank you very much for a very interesting talk. So now the session is open to the questions. Let's see. Maybe taking advantage of being chairman by myself, ask one question. Do you have, okay, this is very interesting. Do you have some insight or some outlook how one can perform braiding actually using this quantum Hall superconductor hybrid structure?
I don't know whether I have the slide. Okay, so I dropped it out slide. Okay, no, I don't think that I have that the slide, but that's very good questions. I think that's probably $500,000 questions. We need kind of a project for doing that. I think basically the one can copy down some of the similarities from the wire experiments. For example, there are T gates or that the multiple gates. So we already started demonstrating that there's a Josephson coupling can happen for this end of this wire. That you can imagine that I can have another one and another one, or maybe you can just have another T-gate type of the things. So you can just kind of copy the idea that has been demonstrated in quantum wires, the semiconductor wires. T-gate, T-wire is a good example, right? So very similar way that if I can create the Majorana fermion or parafermion at the end by just kind of diffusing this or that the diffusing of this type of this to the non-abelian state, there is a braiding operation is possible. The detail one has to work it out. There are a few other schemes, so-called the braiding without braiding, and there are a few other schemes that are out there with nanowires. I think that some of this scheme can be copied down to these features. But of course, as you can see, that we haven't really deeply think about the practical, the next steps, because I think that we need a little bit more the direct evidence first, even before we going for the braiding, because especially the recent events that happens to the semiconducting the Majorana platform, one should be really make sure that we have the solid ground before that we just launch in the next steps. So that's I think important next steps, I believe.
Thank you very much.
Can I ask a question?
Yeah, sure, please.
Philip, great talk again. Thank you. Maybe I'll ask a more broader question over here. What is the speciality or uniqueness of your Parafermion devices as compared to, say, can you make the same device using gallium arsenide quantum wells? Is graphene adding anything unique to this system?
So I think so Parafermion itself is can be in principle kind of work it out in gallium arsenide, and the Parafermion is unique in a sense that has a much more advantage onto the Majorana, which is kind of the Ising Parafermion, I would say. Unfortunately, Parafermion, however, there has been no other material the physics platform can be discussed at least in the theory, other than fractional quantum Hall effect. Basically, you need kind of anyons, and then there's not many anionic system you can create other than the fractional quantum Hall. So unfortunately, you have to work on the fractional quantum Hall for now. Hopefully, that there may be some other system work it out. But then the graphene has a big advantage over the gallium arsenide because the quality is kind of now getting very similar to gallium arsenide. But the important part is basically whether you can make the good transparent contact with the superconductor, especially superconductor which withstand the reasonable high magnetic field. So gallium arsenide is a semiconductor. So when you make the contact with an niobium nitride and this so-called refractory materials, and they tend to develop the Schottky barrier, which actually make the contact loose. Now, however, I would say that there is a good contenders onto the graphene in this way. Indium arsenide, the quality becomes quite higher now, the mobility getting higher, and I think it's very close to seeing that now the fractional quantum Hall effect already, maybe the fractional quantum Hall effect is being started seeing the indium arsenide, and it has been shown that indium arsenide, because of the gap is small, you can make the reasonably good contact with the superconductor. And I believe that in that way, gallium arsenide is probably not easy, but indium arsenide, some of these other semiconductor, which actually you can make the good the contact with the superconductor. I think then it's on the same ground. As long as you get this strong, robust fractional quantum Hall effect and superconducting contact, basically, that's ingrained into what we need. Thank you.
Okay, great. Well, thank you. That was very clear.
Yeah. Okay. All right. Thank you very much. As we are behind the schedule, let's stop. Let's finish the talk for now. Okay. Thank you very much.